the story continues, where we have Kepler's laws that are empirical, seem unrelated to each other. They're weird. Why? And I told you at the end of the last video, who's going to answer that question for us? Yep, our friend Isaac Newton. And so I've probably given a little bit of biographical info about Newton before, but just to get the time frame right, he was born in 1642, Christmas Day, 1642. He had a weird upbringing. His dad died before he was born. His mom remarried the preacher down the street who didn't like anybody else's kids and kind of said he can't live with us. So Newton had to live with somebody. So he largely lived with the local apothecary, the pharmacist. And at one point, he and the pharmacist's daughter kind of liked each other, but that didn't go well. Newton kind of got more interested in other things and ignored her. That was it for relationships for the most part for the rest of his life. And he's a weird guy. But anyway, he's a smart guy. He got to play with chemicals and all, and he got into alchemy and a very serious kid. Everybody knew he was smart. They could tell he was smart, so they sent him off to school. Somehow they came up with the money. He wasn't a poor family. They weren't like rich, but they did have some land, and somehow they scrounged up the money and sent him to Cambridge. And so he was at school. Wow, I just realized something. They didn't have remote learning, but they did have a pandemic. Actually, a little different kind, plague. Newton got started in school, in college. He was off here at Cambridge, and he was doing very well. He was weird, didn't have a lot of friends, but he was doing well. He's kind of in his element. I think he'd been at school about a year and a half, if I remember correctly. Like this, only way worse. They closed school. When like a third of the student body dies, or a third of the town dies, you close school. Now, that school closure lasted, I hope this one doesn't last that long, that school closure lasted a year and a half. So maybe we're going to be a lot better off with this one, and that was a way more deadly thing. By the way, what it was, it was the rats, and the rats had the fleas on them, and the fleas carried bubonic plague, a bacillus bacterium, and so fleas hop off the rat onto you, bite you, and you got the plague. You didn't even catch it from the next person. Maybe you thought you did. Maybe you thought you got it from bad air, and they had those plague doctors with those big weird, I'm not sure they had that in England at that time, but actually, if I recall correctly, one of Newton's contemporaries solved the problem. It was a sanitation-related thing that was drawing the rats and everything. I hope we can solve problems in our day and time. Oh well. Newton has no remote learning. He's on the farm for a year and a half. Maybe they don't give him enough chores to do. I don't know. He sits around. He looks at the moon. Maybe he wonders what holds it up, but not for long, because he figures it's not being held up. You see, Newton is the mind who's figuring out stuff like, that things go in a straight line at a constant speed unless acted on by an unbalanced force. He's already thinking those things as a 19-year-old. Home from the plague at school. Sorry, I kind of get it. This is weird. Any case, he realizes that the moon would go off in a straight line if it weren't for something pulling it into the circle. Nothing holds it up. It's being held down. And he sees apples fall down. Moon falls down. Apples fall down. And he does a lot of math and stuff, and he comes up with some things that I'm gonna like move on with his story here for a second and then bring it back together. But some of the seeds of these ideas are happening already. Hey, it's all on you. During your remote school, you're going to solve the world's problems, aren't you? In any case, the plague passes, partly because they got smart and figured some stuff out. And he goes back to school, and he does well in school. Doesn't do well socially, but he does well in school. And he stays at his school and teaches there. And he becomes a professor. And I've read the story of when one of his supervisors or colleagues or whatever came by to like observe his class. You know, like Mr. Fazen's coming back. I don't know if you've been in the room when he came in, but he'll pop in. The professor came in to check on him, and he was teaching just like I'm doing right now. I'm not, no comparisons with Newton. Okay, not going there. He's teaching, and there's nobody there. He's teaching like I am right now to an empty board or to a board and no students in the room because they were all skipping his class. Thank you for not skipping my class right now. So getting back on track, Newton has this career in his 20s and 30s and into his 40s, and he does some pretty good stuff. He's a really smart guy. He has a theory of light and colors. He thinks that white light consists of all these different colors because he found that white light can be split up by a prism into all those beautiful colors. You've probably seen that before. If not, Google a picture of light going through a prism. It's beautiful. It makes the rainbow. He found you could put the rainbow back together with another prism. He had a theory about little corpuscles of light. He's kind of right, kind of wrong on that. He invented a kind of telescope that I've made several of, Newtonian reflectors. You know what? If that had been all Newton had done, I would have heard of him because I'm into physics. You might have heard of him kind of vaguely, but he wouldn't be super famous because the color thing and the telescope thing that he invented, the reflecting telescope he made, those weren't enough to make him famous. I'll tell you what did in just a second. So he's going through this career. He's now in his 40s, and it's about the year 1680, 1682. I can't remember exactly which year. It's right in there somewhere. And by then, science was sort of picking up in England. And one reason it was picking up in England is Galileo's fate in Italy. Galileo had a student named Torricelli who invented the barometer. You know, he got in trouble with the Inquisition for making an air pressure measuring device. Fine. But you don't go talking much about like what moves around up in the sky, which way it might get a little itchy. England, Henry VIII wanted to get divorced, and the Pope wouldn't let him. So he said, to heck with you, and started his own church so he could get divorced. He chopped a couple of heads off too. Strange history there. But anyway, so the Protestant Reformation happened. The Church of England had been made, and so there's separation. And so the social scientific conditions in, say, Italy weren't in England, and you could kind of do whatever you wanted. And they started having these, there was a society called the Royal Society of London. And all the some of them were professors. Some of them were professors, but some of them were a new class of people like Downton Abbey's upstairs or something, where you got servants to take care of everything else. So you got all day to tinker around because you got money. And some of these people were smart and tinkered around with stuff in their basement. They wanted to share ideas with people. So they'd go down to Royal Society meetings, all get together. They paid dues. The dues would be used for the vote. We're going to publish a book. Like one of the books was The History of Fish. It was some real big, thick book where some member of the Royal Society had like studied carp and bass and every tuna and every fish in the world, put them all in a book. And so they were promoting research and sharing ideas. Newton was a member of it. He'd go to the meetings and generally go right back home after the meetings. He had kind of a friend, Edmund Halley. That's the guy the comet was named after. He also had, there's Newton. We're talking about Newton here. And some other people he knew. One of them is Edmund Halley. Actually, I think they say Hawley. Some people say Halley's Comet. I'll compromise and say Halley. Anyway, so Edmund Halley. There was Robert Hooke. Robert Hooke was a weird guy. Look up Robert Hooke's diary on the internet sometime. You'll see. Some of it's not appropriate. Anyway, Robert Hooke was a rival of Newton. Did not like each other. They couldn't stand each other. Okay, but they'd go to the same meetings, but not socialize. Then there was Christopher Wren. Wren designed a lot of historic London, a big architect. There were other people too. But anyway, these people would all get together and have these meetings. And after the meeting one night, Newton went home like he usually did. And these went to, and I got to tell you, I believe in the truth a lot, so I tell these stories and I mean them to be accurate, but sometimes it turns out I was wrong about something. I used to tell this story a little bit wrong. Let me tell you what I used to say. I used to say that these three, Hallie, Hook, and Wren, went down to the pub. I pictured them after the meeting broke up going out to drink like at a bar. I was wrong. I found out just a few years ago it wasn't a pub. It was a coffee house. You see, coffee, which I only drink about once a year, changed history because up before coffee spread into Europe and around the world, people would get drunk, basically. And they might have fights or something or pass out, but they didn't talk about deep thoughts very much. Coffee goes around, and all of a sudden everybody's getting, like all stimulated and talking deep thoughts and getting excited and whatever. It's just a whole different scene. So there's the coffee house. And what do you talk about at the coffee house? What makes Kepler's laws true? These three are sitting around having a discussion about why in the heck are Kepler's laws even true? These weird laws, what makes them true? And Hallie, I guess maybe, I'm not sure which one said it. Somehow they came up with they were going to have a wager, a bet. Whoever could be the first one to come up with what makes Kepler's laws true wins. Wins what? Their own personal copy of the history of fish. Really tempting, huh? Robert Hooke basically said, I don't know if he said it right then and there at that time or it was over a period of time. Robert Hooke basically said, I know what makes it true. What? I'm not telling you. Why not? I mean, you win a book. I'm going to make you think about it. I'm going to make you think about it, find out how hard it is. So when I finally tell you, you'll know how smart I am. That's what Hooke said. I'm not even kidding. He said that he knew the answer and wasn't going to tell. So he put everybody through the agony of trying to figure it out. And eventually one day, maybe he'll tell them and prove how much smarter he is than them. Really. Anyway, Newton wasn't there at the meeting. Later, Hallie talked to Newton. Newton says, what'd y'all do at the meeting? It might have been letters. I don't know if he spoke in person or if it was letters. But it basically communicated to him that they had this meeting and this bet. And when he said that the bet was what makes Kepler's laws true, Newton says, and I'm paraphrasing, but Newton says, I know that. That's what Hooke said, right? And then Hallie said, pretty much said, that's what Hooke said. Anyway, Hallie says, what? What makes them true? Newton says, inverse square law of central force. By the way, that would be F sub c is proportional to 1 over r squared. I'll explain that in a minute or in a little bit. Anyway, he says that. Hallie says, really? Like, how do you know? Figured it out. When? I was bored during the plague, back on the farm. Not sure those are his exact words, but basically Newton had been sitting on this his entire adult life since remote school, not, since he was off school, and hadn't told anybody. Now, with Newton, it wasn't that he hadn't told anybody because he's trying to taunt them. It's because he wasn't very sociable and he just didn't have it all together. He's kind of all over the place with other things, and he just had never put it together. Hallie said, oh my gosh, this is like earth shaking. You got to tell the world. Newton's probably like, I don't feel like it. And Hallie says, look, I'll be your agent. I'll put up the publishing money. Just do it. Now, Newton, if I had to diagnose, it's a bad habit to diagnose historical figures with things out of the Diagnostic Standards Manual 5 or whatever, like, I mean, you can try to say that, Einstein had ADHD. Maybe he did. I don't know. You can talk about Van Gogh a little bit, probably. But with Newton, Tycho, OCD, right? I guess, maybe. With Newton, maybe bipolar, I'm not sure. Maybe not. But he was definitely prone to bouts of melancholy. And yet, you get him going, he'd go nuts. He went into, whether it's clinical or not, a type of mania. instigated by Halley, waking up the sleeping giant. Newton went crazy, burned the midnight oil and midnight candles, and wrote this magnificent book called Principia. I have a copy of it in my room up there at school. It is incredible. It set the tone for the next 2 centuries. Newton became a legend in his own time. He was knighted. They gave him the job being master of the mint, meaning he got to make money, like literally make money. He probably made money too. But he's a big deal, hugely big deal. Interestingly, there's a thing Newton once said, a couple things. I really like these quotes. I'm not sure I'm going to nail the words exactly, but he said one that was like, if I have seen further than others, is because I have stood on the shoulders of giants. He did have just enough humility to recognize that he couldn't have done all this without all the people who came before. Kepler, for one. Also, he said something about how he felt as all along he was like a child playing at the seashore with the whole ocean knowledge out there, to be seen. I get a little worked up about it. It's a big deal. Okay, so in any case, what did Newton say? What did he do? What did he know? Here's the first thing. The inverse square law of central force. Central force. Newton figured that the sun was pulling on the planets because he's the guy who knows that things left to their own devices go forever in straight lines. He knows if they're not going in a straight line, but they're going in a circle. See why we studied circular motion first? There must be an inward force acting on it, a centripetal force towards the center of the circle, or almost circle. It's an ellipse, actually, close to a circle, perhaps. The sun must be pulling. How? He has no clue how the sun could pull on things, but it must be either that or some crazy conspiratorial force is framing the sun by pushing inward from the outside, but that's pretty weird. Probably the sun doing it. The sun is pulling on the planets with some mysterious invisible force, says Newton. Now, so what does this explain? It actually explains the law of areas. This right here, the centripetalness of it, explains the law of areas. That'll be my shorthand, law of areas. I wish I had some stuff from class that I don't have, but I'm going to tell you what it is. I have this swivelly spinny chair thing. There's actually a stool that other physics teachers keep borrowing and bringing back, and you can spin around on it. And I would do this thing where I would sit there, I'd spin around, and I'd hold some big old heavy books, and I'd hold them out far like that, and then I'd pull them in, and guess what I'd do? I'd start spinning real fast. The news back in 1994, in February of 1994, was not about plagues or viruses or even wars. It was about 2 rival ice skaters, Tonya Harding and Nancy Kerrigan. There was a movie not long ago about Tonya Harding. She's kind of rough around the edges, and she and Tonya Harding were the Americans who were maybe going to compete for the gold medal in the Lillehammer Winter Olympics in Norway in 1994. And she started it, or was her boyfriend acting on her behalf? Her boyfriend hired somebody to come and whack Nancy Kerrigan in the knee and nearly cripple her. Well, actually, she ended up skating after all and getting third. Tonya Harding, didn't get any medal at all. But anyway, it was on the news every night. You'd see Tonya Harding and Nancy Kerrigan spinning, and they pull their legs in. You can't see my leg. It's there. They pull their legs in and go, spin real fast. How do they do that? How do you get spinning fast when you pull things in? It's called conservation of angular momentum. We didn't learn that exactly in this class. We did learn conservation of momentum. There's a spinny version of momentum called angular momentum. And if there's no external torque, twisty force, if all the forces are in or out away from the center, then you will conserve that. And it turns out, I'm not going to do the math for this, but conserving angular momentum is why Tonya Harding or Nancy Kerrigan spin so fast. And it's why the planets go faster when they get closer to the sun. The law of areas again says you got this orbit that varies in distance from the sun. The planet gets going real fast here and it's going to slow there. That's just exactly the down-to-earth same thing as me spinning in my swivelly chair or Tanya or Nancy spinning real fast. It's everyday life. It's earthly, and yet it's heavenly. So that explains the law of areas right there. Then Newton went further. He explained the law of periods. I'm going to do this. I do not know if I'm going to hold you responsible for it, but I feel like I won't have done my job if I don't do it. Just watch, look at it. I want you to get the flavor of it at least. It's one of those things, the derivation thing. Watch this. Okay, so Newton says, and I'm gonna limit this to keep it simple, sort of simple. I can say it's like a circle, just going in a circle. Okay, so centripetal forces are equal to mv squared over r. We learned that. We had a test on that, the Ferris wheel and all that. So then Newton's going like, I want to make sense of the law of periods. Now the law of periods says t squared equals a constant times r cubed. I'll leave the average off because it's going to be a circle and keeps it simple. And then he goes like, wait a minute, I want to talk about the law of periods. There's no v in there. There's a v in here. How can I get rid of my v? I can get rid of the v. Here's how I get rid of the v. You know this. Oh, you're so empowered. V is equal to 2 pi r over t. So he substitutes 2 pi r over t in for v, and he gets 2 pi r over t squared over r. Yeah, a little messy. Equals, comes back over here, equals m times 4 pi squared r squared over t squared r. Out goes one of the r's. Wow. Oh my gosh. T squared? Where have I seen that before? Ooh, it's kr cubed. So he sticks kr cubed in for t squared. He gets m times 4 pi squared r over kr cubed. Out goes one of the r's. And I can rewrite this as 4 pi squared m over k times 1 over r squared. This is a constant. Remember, a bunch of stuff that doesn't change. It's a constant. Fishy sign means equals a constant times. This is all a constant. There, I just performed for you a simplified version of Newton's proof that the law of periods is a direct consequence of the sun not only pulling on the planets, but pulling on the planets with a force whose strength, wow, it's all tying together. You know what? First week of school. Tai Chi stuff, remember all that? Inverse square law. -2 power, that one. The kind of thing where when you get twice as far away, you drop to 1/4 of the strength. That's like, you might have felt something like that if you've ever played with magnets. It's like you get them closer together, they pull harder, and you get them further away, it's weaker, but it's dramatic. It's like when you get them half as far apart, they pull something like 4 times as hard. It's like, oh, this ain't nothing, this ain't nothing, whoa, like that. Same thing here. It's a dramatically changing strength of the force. When you get a little closer, it gets a lot stronger. And it's mathematically described, like we did the first week of school, is an inverse square law, 1 over r squared, the -2 power. I taught you that for a reason. Looking ahead, way ahead. So this explained the law of periods. So we explained the law of areas with the Tanya Harding thing and the conservation of angular momentum. We've explained the law of elliptical orbits with the inverse square thing. And the thing that I would show you with my program, if I could run the program for you, but I can't from here, I would show you that only when power of r is -2 in my program does it make elliptical orbits with the sun at one focus. There's other powers of r, like other parallel universes you can do, like power of r1. It makes ellipses with the sun at the center. Some of them make spirals, crazy shapes. There's these beautiful star-like patterns you get with the 5 power. Parallel universes of other kind of laws of physics. but they ain't what we got here. This is what we got here, and look what he's done. Isaac Newton has just taken Kepler's 3 weird, unrelated laws and showed that they obey the golden rule that the sun pulls with a force that drops off real fast with distance like that. That's it. He solved the mysteries of the solar system by saying the sun pulls like that. That's huge. Hey, if that's all he did, he'd be like, I would have known a lot about him, and you probably pretty sure would have heard of him. He'd be getting kind of fairly famous, but he still wouldn't be the giant that we think of him as, because there's more. Let me finish this story. So he's just found out that the planets go around the sun the way they do because the sun pulls with a force towards itself, centripetal, that acts like this mathematically in string. But what about Jupiter's moons going around Jupiter? They go around Jupiter. Wonder why they would do that. Oh, maybe Jupiter pulls on them. Maybe Jupiter pulls on them with a force that's like this. Like if you got twice as far from Jupiter, it'd be a fourth as strong. 3 times as far, it's a ninth as strong. Maybe it does. He checked the periods of Jupiter's moons, and you know what? Nailed it. They obey Kepler's laws. In other words, he hadn't just explained the planets go around the sun. My gosh, he's explained Jupiter's moons go around Jupiter. And guess what? Saturn's got moons. They knew by then. You've probably seen them. Saturn's moons go around Saturn with this period. Wow, like everybody's doing it. The sun's doing it, Jupiter's doing it, Saturn's doing it. Guess who else might be doing it? The Earth. The Earth might be doing it and pulling on the moon and making the moon go around the Earth in an elliptical orbit with maybe the Earth pretty much at one focus and maybe sweeping out equal areas and equal times. And yes, it did. You might wonder if the moon obeys the law of periods. Now, there's only one moon, so you can't finish the graph. I mean, it's kind of hard to take a graph and say that it's that curve because it goes to that point. If we had lots of moons, you could do that. But the bottom line is, Newton is starting to realize that bodies all over the universe, ooh, new word, universe, bodies all over the universe are apparently doing this. The sun's doing it, Jupiter's doing it, Saturn's doing it, maybe the Earth's doing it, but is the Earth really doing it? Is the Earth really pulling on things like the moon? Oh, it pulls on apples. It pulls on the moon, it pulls on apples. Do you realize this when he's 19 during the plague? So, let's see how this works out. I got a few more minutes in this video. Can't stop now. Gross. Good enough, I guess. So here's the deal. Newton decides to compare the acceleration of an apple to the acceleration of the moon with the hunch, the suspicion that they're doing it for the same reason. Now, you know the acceleration of an apple, so did Newton. Even though he didn't use these units, he had his own units. So he probably used feet and stuff. But anyway, the acceleration of an apple is well known. 9.8 meters per second per second. Newton has a hunch about what the acceleration of the moon ought to be. The acceleration of the moon ought to, you think it ought to be this? I asked this question. If you were here, I'd ask the question. Is the acceleration of the moon supposed to be the same as an apple, 9.8 meters per second per second? Heck no, Newton doesn't think that. He thinks it's for the same reason, but it's not the same amount because he thinks it's an inverse square law, and the moon is terribly much further away. You see, here's the radius of the Earth, and there's an apple, and the apple's like a radius of the Earth plus maybe 20 feet high of the tree from the center of the Earth. And he figures the center is where you should measure from. He invented calculus to prove that was right. Yeah, that's his fault. And a German guy named Leibniz. Anyway, the moon is way further away, and he knew this. He knew the moon was 60 times as far from the center of the Earth as an apple is. And he figured the force, if the Earth is really doing this to the moon and apples, that force should diminish greatly by the time it gets 60 times further away. So in fact, he doesn't think the acceleration of the moon is 9.8. He thinks it's 9.8 divided by 60 squared because it's 60 times further away, and he thinks it's an inverse square. It's a hunch. He doesn't know it yet. He's got to plug in the numbers. He plugs in the numbers and gets 0.00273, I think it is. You could actually check that. It's something like that. Meters per second squared. And then he knows the moon's orbital period, how fast it's going, how far away it is, and he plugs in the numbers, and guess what he gets for the moon's actual real life acceleration? He gets that. See, it's not just that he calculated what the moon's acceleration ought to be. Well, that's nice. It's calculation. The point is not that he calculated, it's he calculated and compared it to real life, and it was the same. Wow. Newton has just invented the universe. Now, I didn't say he created it. He establishes the concept of a universe where the heavens and the earth have been united, acting under the same cosmic force. Before, the heavens were the heavens, the earth was the earth. Newton has shown that common everyday things like gravity, like an apple falling, that's the same thing that guides the planets. Maybe you knew this. Good for you if you did. People didn't, though. This is a new idea. Now you have a universe united like that. Now, I'll mention in passing, Newton was also fancying himself quite the theologian. He actually wrote more words about theology, about the Bible and everything than he did. He had some slightly controversial ideas at the time, but he still was super important to him. And so he actually thought that, you know, the universe, all of creation, ought to be under the influence of the same force because it all had the same creator. So that is one of his ideas that helped motivate him to think this. Regardless of what your opinions are on that, that is something that did influence him. So in any case, you got a universe now. But what gives you the right to do this? How are you going to, why would you go around pulling on things? What magic, what dark magic do you use to do this? Well, the word is gravity. Because the word was already around for like gravity, yeah, like things fall. But gravity now is a lot more than like things fall. Gravity is like this universal force. What gives something the power to do it? Turns out, I got it, you got it. We all got the power. Because all you need is mass. Because Newton realizes an object that's 10 times as heavy falls the same. It must be pulled on 10 times as hard, but on what? On its mass. So here, I'm going to wrap up in a second, and I'll run a little over 30 minutes right here. So basically, you got the force that he's now going to call gravity. What's calling it centripetal? That's gravity. The force of gravity is proportional to 1 over r squared. It's also proportional to the mass of the victim and the mass of the perpetrator. And actually, it takes 2 to tango. I don't care which one's the victim, which one's the perpetrator. It's 2 masses, M1 and M2. And their distance apart r. And they pull on each other with a force. When you put it all together, this is back to the first week of school. It's proportional to, oh God, I blew it. Yikes. I hope you didn't stop the video right there. I hope you didn't. No, it's M1 and M2. God, blew it. Okay, M1, M2 over r squared. I'm in a hurry. And then he says there's a constant. It's big G for gravity, gravitation constant. That is what, there, I finally did it. You see, this is where in a lot of physics classes, we start this whole unit. They just started with that. They said, in 1684, Isaac Newton published his famous formula, F sub G equals Gm1 over M2, M1, M2 over R squared. And then let's do some problems. Okay, so I just wasted a week or 2, right? No, ain't no waste. We're going to come back and use that thing. Yeah, the math is back. Happy calculator. So I told the story. Watch it again if you want. And I hope you fix the error I made. Bye.